So what I'm going to do here, first, I'm going to say that for the sake of simplicity, okay, and much like here in front of the whiteboard, okay, we're just thinking of motion in terms of one dimension, okay. So this is all one-dimensional. What that means is you can only go, you can only move, say, back and forth, or left and right, or up and down. Everything is, there's no other way, other place that I could move in, okay? And what we're going to say is displacement, we're going to call it x. Because that is our letter of choice, our pronoun of choice when we're talking about unknowns, okay? Now, if we say, okay, I want to think about the displacement of this mandarin, okay? Now, is anyone got a stopwatch on them? Anyone got a stopwatch on them? I don't know if I can throw this. I don't know if this ceiling is high enough. I suspect it's not going to be. But it's sorry, Joe, you might go without your. No, okay. Jaffley, I want you to time how long it takes between the mandarin leaving my hand and me catching it. Okay, you ready?
Human error.
We're just okay on the count of three. Okay, 1, 2, 3. How long was that?
93 milliseconds.
Wow, that was not very long. 90 milliseconds?
Milliseconds?
What is this?
Milliseconds? That doesn't sound right. Because wasn't that close to a second? I think that's 930 milliseconds, isn't it? What's a millisecond? Isn't a millisecond a thousandth of a... Milliseconds is...
Less than a second. Like, it's the next stage down from 1 second.
Really?
Well, it is milliseconds, but I think it's 930. Because didn't that feel like about a second?
Yeah.
It's about a second, right?
Well, yeah.
We use the
Actually, wait, really? I thought it was 93 milliseconds. Wait,
Milli is like...
Meter. Wait,
It's 1,000, okay? I'm telling you.
second?
Okay, let me try and... I wanted it to be a little longer, so let me try and throw it a bit harder. Can you time for me again? Okay, you ready? Maybe if I go a bit lower.
Okay, yeah, I'm ready.
Sorry?
No, I said you.
Oh, yeah, okay, alright. So you ready? Okay. This is going to be dangerous. Okay, on the count of 3. 1, 2, 3. Okay, how long was that?
142.
Yeah, that'll do. Okay, let's deal with it in, okay, you can, no, I'm going to hold on to it. I might need this. I might get hungry, okay. Let's call it,
Rigorous exercise.
can I call it 15? Is that okay? It's just an easier number. Okay. Let's call it, just so that we can deal with like integers and stuff like that, okay? I'm thinking of time as t, okay? So I should have said time is equal to t. Okay. I'm going to go in tenths of a second. Is that okay? Tenths of a second, because that'll give me integers, okay? So a tenth is like what? A deci? A decasecond.
Yeah.
Okay. Deca or deci? Which one is it? Decimal, decimate, it's 1 in 10. I think it's deci. Surely someone can look this up, but anyway.
I think deca is just times 2.
If you like, you could just forget what unit it is, and we could just call it time units. Okay? Okay, so here's what we knew. Okay, at time 0. Actually, let's draw. I want to just draw up a really brief table. Okay, so I've got time, and I've got x as my displacement. Okay, as I started, let's call my hand, wherever my hand was, down below. Let's call that the origin. Okay, that's where displacement is equal to 0. That's where we begin. Okay. Now, I think let's go to 14 because even is actually better. 14 deci seconds, time units later, okay, it comes back, right? Now, when was it? When was the mandarin? When was the mandarin highest? Okay. I assume it was halfway, right? Based on the fact that when I throw it up, it takes the same amount of time to go up as it does to go down. Okay. So at 7. Don't get me into air resistance, okay? And all that. At 7 now, how far to go? I don't know how close you got to the ceiling. What do you want to call it?
2 meters.
2 meters? Well, hold on a second. I'm like
Oh, wait.
1.78, I think. I'm just short of 6 foot, I think. So it went at least twice as high as me, right?
You use physics for this.
I don't know. 3 meters? Should we call 3? 3?
We figure out the
I know.
2 of you got the head.
2 of you got the head. That's a great way to visualize it, isn't it? Okay. Just shut my head off and then put another one on top. Why do I ask these questions? Okay. I'm going to call it 3 meters. Okay. Now, by the way, take note. Okay. If I had dropped the mandarin, okay, it could have gone negative, right? Because we're thinking about displacement, so that includes direction, so it could have gone down. You know, if it was like a mandarin made out of, I don't know, what's something dense? Like lead. Or it had to be denser than lead. If I just dropped lead, it would just hit the ground. But if it was like, you know, the density of a black hole or neutron, it just like go through the ground or something like that. So it could go negative, okay, in some situation. Okay, now, I could have more information, right, in terms of like what happens in between here, what happens in between here. We could have taken a physics sort of approach to it. That's what we've done, like observe it, right? But now I want to enter the realm of the mathematician because this is actually enough for us. This is enough, okay? Because if you think about this, this is a displacement, x, is a function of time. Okay? So you could write it like this. So the question is, what kind of function is it? And mathematically, it doesn't take that much imagination to think, well, what kind of shape was it? It went up, and it was fastest when I released it, and then at the top, it slowed down, and then it came back. So the shape it draws out is a parabola, right? Except it's sort of a parabola, sort of not, because it just goes up and down, right? So in terms of motion, it's just on one dimension. But if you think about time, all right, so let's draw this thing, shall we? Now, this is confusing, because x is up there. X is our vertical axis, okay? Now that maybe makes sense for us because we're actually thinking about up and downs, that's okay. But later on, x might be left or right, or back and forth or whatever, and it will always be this vertical axis, okay? So there's a bit of a shift right away. Okay, now, we said it goes up, and then it hits 3, okay? And then it comes back down. And the whole journey took 14 time units. So I've got 7 in the middle there. Okay. Now this is a section of a parabola, okay, and that, because we're just imagining this, it doesn't have to be real, perfectly accurate, because it's true, because of like, if you were a physicist, right, you'd have to worry about the fact that this part and this part would not be exactly equal, because there's like other factors involved, okay? But as a mathematician, I can be like, I'm just going to call them equal. I'm going to make it a perfectly symmetrical object, okay? What is its equation? What is its equation? I want x equals something. Okay, I've got intercepts, right? I've got an intercept 0 and one at 14. Okay, so how would I start to write out my equation? Okay, now that'll give me the roots in the right spot, the 0 and the 14. Okay, but there's something else I haven't taken into account, namely how high it went. Right? So how do I factor in the point that this is 7, 3? How do I do this? So I want to test out, well, okay, when t equals 7, right, I want it to equal 3. Okay? What happens with this equation? Well, at the moment, x will equal 7 times 7 minus 14. Minus 49? Something has gone wrong. What's gone wrong? A few things have gone wrong. Hold on a second. This thing has the right roots. It's got 0 and 14. Okay? But, so it's upside down. Okay? Because, that makes sense. This thing is concave up, right? So this is the wrong kind of parabola, right? How should I fix that? Slap a minus sign on it. Okay, good. Now, what effect does that have here? Minus sign, that's positive. I still don't have exactly what I want, so how am I going to adjust it? It's 49, which, you know, I'd like to think that I have a good arm, but it's not that good. So I need to adjust that, I need to ratchet that down, okay? So how am I going to adjust this original equation such that this becomes 3, not 49? I could subtract 46. But that would give me some problems, right? Because when you have a graph and you subtract a constant from it, what effect does that have on the graph? It moves it up and down. So if I just move it 46 units down, okay, the roots are also going to move, okay? So a constant, unfortunately, will not do, okay? Now, take another step back. Let's just imagine, what is this equation? What does it look like? Well, we've said it's 49, so it looks like this. Yeah. So in terms of shape, it's exactly right, but it's off not by position but by scale, right? It's too tall. Okay, so how do I squash it down? If you had a line and you wanted to make it smaller and gradient, what would you do? It's about the coefficient, isn't it? Right? Like I'm worried this thing is too steep. Okay, like this is actually like this, and I want it to just be that. Right? So therefore, I still want these intercepts to stay put. So I'm going to multiply it by, I'll put this out the front, minus 3 on 49. Okay? Can you see what that's going to do? It's going to divide that number by 49 and then multiply by 3, which will land it exactly where I wanted it. Okay? So now I've got these values right. Okay.